We've spent a few days here now on impulse. Yesterday we extended it a little bit to talk about impulse experienced by two different objects in a collision between those two objects. We said yesterday that if two objects do collide with each other, it doesn't matter how heavy the objects are. Maybe they're equal mass, maybe they're not. It doesn't matter how fast they're moving. Maybe they're equal speed, maybe they're not. It doesn't matter what direction they're moving. Maybe they're going in the same direction. Maybe it's a head-on collision. It doesn't make any difference, any of that stuff. If one object collides with another object, object 1 and object 2, then object 1 will experience a certain change in momentum. Object 2 will always experience exactly equal to that, but opposite in direction, the same impulse, the same change in momentum. So, for instance, if person number 1 is running down the hallway and collides with person number 2, and person number 1 loses 5 units of momentum, then person number 2 must automatically gain 5 units of momentum. If a train barreling down the track happens to hit a car that's crossing at the crossing, if the train gains 10,000 units of momentum, then if the car gains 10,000 units, then the train must lose 10,000 units. The car's impulse would be positive 10,000. The train's impulse would be negative 10,000. That will always be the case. It doesn't matter that the train is way heavier than the car. It doesn't matter that the train is moving faster or slower or whatever than the car. It doesn't matter what the directions were. If one gains 10,000, the other has to lose 10,000. Now, the impulses are the same. What else is the same? This is a physics 20 question right now. What else besides the impulse will always be the same in magnitude, but opposite in direction? The force. Yeah, if the impulse experienced by both will be equal and opposite, so will the force be equal and opposite. Finally, the last thing that we said yesterday was that if you're analyzing a situation like this, where there are two objects interacting with each other like this, and you're solving it as an impulse problem, then you got to make sure that you pick one object. We did an example problem yesterday where we had two cars colliding, and we wanted to find the force of impact on one of those objects, on one of those cars. Well, we picked one. We had data for both, but we picked one of them because that's what you got to do. You can't use the mass for one and the final velocity for one, but the initial velocity for the other one. And you got to be consistent. Pick an object, stick with it. Got it? All right. Today what I want to do is go a little bit further with impulse still. This will be our last quantitative aspect of impulse. Tomorrow we'll start taking a look at a little bit of qualitative aspect of impulse, okay, explaining some situations as opposed to calculating some numbers. Today I want to look specifically at what we call force versus time graphs, or impulse graphs. The graph that I'm talking about would usually look like this. We see force on the y-axis and time on the x-axis. Earlier on, I told you guys when you see a funny angle like 30 degrees, you should always think 5 words. I don't like funny angles. And then go with that. Get rid of the funny angle by using sine and or cosine. Okay, I'm going to tell you one more little phrase that I want you to remember now. Every time you see a force versus time graph, I want you to think 3 words. This one's easier because it's only 3 words. Area equals impulse. Always. Now, it doesn't mean you're necessarily solving for impulse in one of these graphs, but you will always think area equals impulse. Because even if you're not solving for impulse, you're still going to go through that process of getting impulse before you can get what you want. So the graph may look like this. We calculate that impulse, sorry, we calculate that area will represent the impulse, the area between the line and the x-axis. Now, a lot of times, I'd probably say 3/4 of the time, the graph will look like this, where the line is entirely above the x-axis. But sometimes, maybe 1/4 of the time, goes like this. Well, we can still find this area as well, right? The difference is here that the green area above the x-axis is a positive impulse because it's produced by a positive force. It's a gain in momentum, right? A positive force causes the object to speed up, a gain in momentum. But the area down here, the impulse down here, would be a negative impulse because a negative force produces a loss of momentum. A force in the opposite direction causes something to slow down and lose momentum. Whenever you see this graph, whatever the shape, above the x-axis, below the x-axis, think area equals impulse. And then let's get a little bit more specific. Above the x-axis, positive, below the x-axis, negative, and add them all together. Add them all together. If the total area is positive, it's a gain of momentum. If the total area is negative, then it's a loss of momentum. And finally, you won't necessarily be asked to solve for the impulse. You are a lot of times asked just to solve for impulse. And if that's the case, then all you got to remember is those three words, area equals impulse. But you may also be asked to solve for, say, the change in velocity of the object. Don't change anything that we've just done. Regardless of what you're asked for, think area equals impulse. But if you're asked for change in velocity, then go a step further. Get area equals impulse, and then use the equation delta P is equal to m times delta V. Right? This is area, right? The area that you just found, the impulse, is equal to the mass times the change in velocity. Do not use, I repeat, do not use this equation. Why not? Why do you think I don't want to use F times T? It's technically valid. Like it's not a wrong equation. I'm just telling you, don't bother trying because you're probably going to mess up if you try to use it. Anybody know why? Yep.
Not already just finding the area.
Well, it is, but so is this. Right? Presumably, if we were going to try this equation, we would have already found the area, and then we'd be solving for something in here, right? Yep. Yeah, that's the thing. F stands for the average force. Well, tell me what the average force is in this one. Like, I have no idea. I have no idea what the average force is there. So don't even bother trying. It's valid if you know what the average force is, but we usually don't, so don't even bother. Yeah, I'm telling you, if you remember area equals impulse, and you use this in conjunction with it, you'll get what you need every time. You don't need to bother trying F times delta T, even if it is technically valid. All right, the only example that I want to do with this is on page 462. It says a golfer hits a long drive sending a 45.9 gram golf ball due east. Figure 9.22 shows an approximation of the net force as a function of time for the collision between the golf club and the ball. What's the impulse? And what's the velocity of the ball at the moment the golf club and ball separate? Let's go over here to the picture. Oh, look at that. Look at what we got there. A force versus time graph with milliseconds on the x-axis, which we don't want. Force versus time. Three words should come to your mind right now for everybody. What are those three words? Yeah, well, it's one of them. What are the other two words? Area equals? Yeah, area equals impulse. Now, regardless of what we're asked for, that's what we want to be thinking. Area equals impulse. So let's get the area. This is a triangle. So the area of this triangle that is equal to the impulse is simply going to be 1/2 base times height. The base goes from 0.1 to 1.1. So the base is 1.0 times 10 to the minus 3, because it's milliseconds, times a height of 5,000 newtons. because it's an area or an impulse of 2.5 Newton seconds or kilograms meters per second. Look, without even really thinking about it, we just solved for A. The impulse provided to the ball is 2.5. We did that just because we automatically think area equals impulse. What's the velocity of the ball the moment the golf club and ball separate? Well, there's only one other thing I can do here. Let's rearrange this equation to solve for delta V. The mass is 0.0459. I'm not going to forget that because I circled it. It was 54.5, I think, meters per second. I've just solved for the change in velocity here, technically. I'm looking for the final velocity. But tell me, what was the initial velocity? Okay, 0. So if the change is 54.5 and the initial is 0, then the final, which is what I'm looking for, is 54.5. All right, this is it for today. Please do for homework, page 462, the questions that go along with that practice, that example problem. Page 462, number 1 and 2. In addition to practice question set 2A that is now posted on Google Classroom. I believe there's 4 or 5 multiple choice questions that, just like last time, you're going to submit electronically. Okay, do these 2 questions and then these 4 or 5 questions, and that's going to help us in preparation for our quiz on Friday on impulse.